Cross-site scripting, or XSS in short, is one of the most dangerous attacks on the web. XSS vulnerabilities are prevalent in many applications. Also, the impact of an attack on the application is quite severe. Here we investigate two common XSS attack scenarios. But before we dive into the details, let's take a look at the consequences of a cross-site scripting attack. An XSS vulnerability allows an attacker to get a foothold in the application's browsing context. The typical demonstration of a vulnerability is popping up an alert dialog. Ironically, this is one of the most harmless consequences of an XSS attack. The alert box only visualizes the presence of an attack vector. In reality, the consequences of an XSS attack are a lot more dangerous. One example is the defacement of a page, a technique often used by politically motivated hackers. Another example is the theft of sensitive information stored in cookies or browser storage mechanisms. Such theft can even escalate into a session hijacking attack. These examples are scary, but the attacker possesses the full power of JavaScript, so nothing prevents him from injecting a more elaborate payload. Examples are keyloggers, network scanners, or well-crafted social engineering attacks. And then there's Beef, the browser exploitation framework. This framework offers a command and control interface. Once the attacker has hooked the browser, he can execute all kinds of commands with the click of a button. So far, we have established the significant danger of cross-site scripting attacks. Let's take a closer look at how these attacks work in practice. Earlier, we already discussed an example of a script injection attack. In the attack, the payload is sent to the server as part of the request data. The server incorporates the payload into the HTML page of the response. When the browser processes the page, it sees the payload data and mistakes it for code. This mistake results in the execution of malicious code. This type of attack is known as reflected cross-site scripting. At first, this attack scenario seems irrelevant. Users are unlikely to attack themselves, but when the attacker manages to send this request from the victim's browser, then the malicious code will be executed there. Using such a reflected XSS attack, the attacker can run code in the victim's browser. This gives him full control over the application's browsing context. As a result, the attacker can steal or manipulate information and even impersonate the victim. Let's take another look at how this works in practice. The attacker embeds a hidden iframe in the unrelated page. By setting the URL of the frame, the attacker can trigger a request to the search feature of the BeerSafe application. The attack payload is part of the search query sent to the server. The application responds with a page with the search results. The top of the page displays the string that the user searched for. As you can see, it also includes the payload that the attacker injected. When the browser renders the page in the iframe, it interprets the payload as code and executes it. Using this XSS vulnerability, the attacker can run arbitrary script code in the BeerSafe context. This code runs in the user's browser, using the user session with the BeerSafe application. As you can see, the fundamental property of a reflected cross-site scripting attack is the presence of the payload in the request. This scenario is where the name cross-site scripting originated. A request with a payload going from one site to another, resulting in the execution of the injected script code. Today, the name XSS covers a lot more. The best example is a stored cross-site scripting attack. In this scenario, the attacker injects the payload into the application's database. Whenever a user visits a page that displays this data, the payload will be embedded in the page. When the user's browser renders this page, it also executes the attacker's code. Here is a practical scenario of a stored cross-site scripting attack. The attacker can use the BeerSafe application to submit tasting notes. But here, the attacker embeds a piece of script code into one of the tasting notes. The BeerSafe application stores these notes in the database, including the injected script code. The actual injection happens when another user requests these tasting notes. The BeerSafe application queries the database to retrieve a list of tasting notes. With this list, it builds the HTML page to send as a response. As you can see, the HTML page contains the legitimate tasting notes, but also the injected code. Like before, when the browser encounters the code in the notes, it mistakes it for legitimate code and executes it. The defining property of a stored cross-site scripting attack is the presence of the payload in the application's data store. Note that this attack does not involve a cross-site request and is executed entirely within the targeted application. Each of these scenarios has a different approach, but the result is the same. Both enable the execution of the attacker's code in the victim's browser, inside the application's context. These attacks succeed because the browser lacks the context to distinguish between data and code. So how can we defend our application against these script injection attacks? That's what we will cover next.